Welcome to channel's YouTube intro Ramat. In today's explainer, we're diving into a genuinely fascinating technical mystery. We're going to look at how one single developer managed to completely break the golden rule of local AI hardware constraints, literally allowing these absolute giants to run on everyday consumer machines. To really wrap your head around the scale of this breakthrough, I want you to imagine trying to load a massive AI model. We're talking specifically about the 744 billion parameter GLM 5.2 model. Even when you heavily compress this thing down to 4-bit precision, the weights still take up a staggering 370 gigabytes of disk space. So looking at that number, it sounds mathematically impossible to run it on normal hardware, right? Yet, right now, this colossal model is running smoothly on a modest 25 gigabyte machine. No expensive graphics cards, zero. And it's doing it using a pure C engine with no external dependencies called Colibri, which is Italian for hummingbird. This entire breakthrough rests on a single, massive paradigm shift. See, basically every other tool out there assumes that if a model doesn't fit into your memory, you just can't run it. But Colibri changes the fundamental question. The model doesn't actually have to be completely in memory all at once. It just needs to be intelligently placed. Section 1. Fit versus place, a new paradigm. Let's dive right into this and explore why we really need to stop trying to force massive models to shrink. Traditionally, the industry gives us two pretty bad options, right? The old rule dictates that you either shrink the model until it fits, which means you're quietly losing intelligence and quality, or you drop thousands of dollars on a massive stack of GPUs. But Colibri introduces a completely new rule. Think of it like a hyper-efficient librarian. It keeps the full quality but brilliantly manages exactly where every single piece of data lives at any given millisecond. Now, this magic works primarily because the GLM 5.2 model uses an architecture called a mixture of experts. Inside this massive 744 billion parameter brain, there are actually 19,456 smaller specialized networks. But for every single token generated, the router only activates a tiny handful of them. And this perfectly illustrates the math behind the magic. The dense shared part of the model, the part every token needs, is just under 10 gigabytes. And the specific expert parts that actually change from one token to the next, that's only about 11 gigabytes. So, out of a 370 gigabyte behemoth, the moving parts you actually need at any one time easily fit into standard RAM. To handle this flawlessly, Colibri visualizes your machine as 3 distinct shelves of memory. Your ultra-fast VRAM on a graphics card is the top shelf. Your modest, standard system RAM is the middle shelf, and your huge, comparatively slow solid-state drive is the bottom shelf. While most AI engines treat hitting that bottom shelf as a complete failure, Colibri treats it as a first-class citizen. Section 2. The 5-step engine. Per token pipeline. Every single time a token is generated, Colibri follows an incredibly elegant operational sequence. First, it routes to pick the needed experts. Next, it performs a union, merging those requests so no expert is ever fetched twice. Then, it places them on the best available shelf. Fourth, it overlaps, computing the data it already has while loading the missing pieces in the background. And finally, it actually learns what you used so it can adapt for the very next run. Section 3. Cheating the slow disk. Overcoming limits. Obviously, the biggest bottleneck here is hitting that bottom shelf. Relying on a slow SSD should, in theory, totally ruin performance, but Colibri cheats those wait times using 4 specific moves, ensuring it almost never waits for the disk twice. It stores wait matrices right next to each other for single-seek reads. It uses an asynchronous I/O pool so your CPU never just sits there idling. It uses batch union so unique experts only cross the slow disk boundary once. But honestly, the true genius lies in the 4th move, the pilot. This pilot thread is absolutely fascinating. It constantly looks ahead and pre-fetches data before it's even needed. And why does this work? Because the developers did the math and discovered that expert routing is actually 71.6% predictable. So most of the data your system needs is already making its way up those shelves before the engine even asks for it. And thanks to its unique learning cache, Colibri records exactly which experts your specific workload uses most. If you're mostly asking coding questions, it pins those specific coding experts to your fast RAM. The engine literally reshapes its memory around your work. It feels alive, because the more you use it, the faster it gets, ensuring your hottest data never touches the slow disk again. Section 4. Proof and performance speeds, displacement prost. So you might be wondering, with all this clever streaming, caching, and shuffling around between disks and RAM, does this placement strategy cost us any of the model's actual intelligence? The answer is a rigorous, mathematically proven no. Extensive tests show that Calibri's output is 100% token exact to the original reference implementation. That means dropping down to a slow memory shelf might cost you a couple of seconds of generation time, but it will never, ever cost you a single ounce of precision.
Actually, there is one vital engineering gotcha you've got to keep in mind. GLM 5.2 includes a draft head that basically guesses tokens ahead of time for free speed. The community figured out that if you compress this specific part to 4-bit, the guesses silently fail and just become pure overhead. The rule is simple here. That draft head must remain at 8-bit quantitation, so a lower compression level, for the speculation to actually work correctly.
When we look at the real-world speed ladder, it's remarkably honest. On a Cold's 25GB RAM box relying mostly on the disk, you get about 0.1 tokens a second. Move up to a 128GB CPU box, and you're getting nearly 2 tokens a second. Throw in a top-tier RTX 5090 graphics card, where the experts fit easily into VRAM, and you're suddenly scaling to nearly 7 tokens a second. But here is the beautiful payoff of this whole placement philosophy. You're looking at the exact same engine and the exact same model weights across all of those devices. You don't have to download a special light version for your laptop. Hardware upgrades don't change the model. They simply allow you to move the experts up to a faster shelf. Section 5. Try it at home. Run Colibri locally. Testing this architectural marvel on your own machine is incredibly straightforward and, best of all, entirely free from those usual dependency nightmares. Since it's pure C, you just clone the repository and run a single setup file. It checks your compiler and builds the engine instantly. Right out of the gate, you unlock powerful built-in tools like ColliServe, which spins up an OpenAI-compatible API. This means you can interact with this local giant using any tool or UI you already love. But if you want a real treat, the Colli web dashboard is absolutely breathtaking. It gives you this 3D living visual cortex right in your browser. You can literally watch the thousands of experts cluster together by topic, like poetry or code, and watch them flash, fire, and reorganize themselves based on your queries in real time. It is so cool to see. Ultimately, Colibri proves definitively that these monumental AI models aren't forever restricted to million-dollar data centers. They belong on any desk that can smartly manage its memory hierarchy. The ceiling on local AI was never really your hardware. It has always been about how we place the data. I highly recommend opening your terminal and running the simple read-only Colali Doctor command on your computer today. It doesn't download any massive files, but it maps out exactly how your current hardware could place these giant models. So discover just how much power you've been artificially locked out of, and ask yourself, what impossible model are you going to place on your desk next?